Hello everyone, my name is Jason Gregson, and welcome to the next video in your Calculus 2 video set. Today we're going to talk about section 8.2 on surface area. So let's get started. Now, before we launch into surface area, though, I want to do a quick review of just general integration application. So how do we actually get values by taking integral? We'll start once again with area like we did in the last section. So if I want to find the area under the curve from 1 to 5, what I would do is I would look at a small slice. So I cut a small slice, and I approximate the area in just that slice. In this case, I'll call that delta A. And I'll say that's approximately the height at some point in that interval times the thickness of the interval, which I'll call delta X. The next thing I would do is I would find the approximation for the total area by adding up all my slices. And then I want to find the exact value, so I would look at the limit as delta X goes to 0 of that sum. And then lastly, I would recognize that as the definition of the definite integral. And so the area in the curve would be the integral from 1 to 5. Now we've seen that before. I want to go through it one more time, kind of from more of a heuristic approach. The idea is I could do this all with sort of differential notation. I could say what's an approximation for the area in this little slice? Call it dA, and then I take the height there times a little change in the x value, that dx for the thickness. And if I want to find the total area, I would add up all those slices continuously, which is what I'm doing with that integration. It's really taking the limit of that sum. So I'm going to call that adding up all my slices continuously. Let's look at one more example. Last time we looked at arc length. We have the same basic approach. I want to find the length of the curve from x equals 1 all the way over to x equals 5. How do I do that? Well, I cut a small slice. There's my small slice. I'm going to call that a small slice of arc length, ds. And I want to approximate the value of the length of that arc inside this small interval. And so last time we talked about how we can look at that little dx value, that little dy value, and we can use Pythag to get an expression for a little slice of that arc length. We can say this is the square root of dx squared plus dy squared, like that. And then a little bit of algebra gave us the square root of 1 plus dy dx squared, so the derivative of y with respect to x dx. And another piece of algebra, we could have chose to represent this as 1 plus dx dy squared dy. So this would be appropriate if we had x as a function of y, and then we could calculate the derivative of x with respect to y. And whichever way we choose to represent our curve and thus our piece of arc length, we would find the total arc length just by adding up all these slices continuously. So we could either generate this formula for arc length, or if we add up all the other slices continuously, we can get this expression for arc length. And once again, the big idea is cutting a slice, approximating the value inside of the slice, adding them all up continuously with integration. All right, so now let's look at surface area. Okay, surface area. So now I have this curve. I'm going to rotate this curve about the x-axis. So I'll get kind of its mirror image over here. And the idea is I'm taking this point and I'm rotating it about the x-axis all the way around, kind of generating the circle here, rotating it about. And if I did that for all the points, I would generate a surface. I want to find the area of this surface. So I don't know how to do this. So what could I do? I would cut a slice of this surface area out. Here's me cutting a slice. I try to approximate the surface area of my slice. Now the first thing I need to do is find out what the shape of my slice is. And so I might first say, well, this kind of looks like a cylinder. But I got to be a little more careful here, because really I'm not approximating this edge to be a horizontal line. Rather, I'm approximating with a straight line. So just a little straight line along this curve. In fact, that's going to be a little piece of my arc length. So in that case, my slice isn't going to be a small cylinder, but rather a small frustum. So I have a straight edge here, and a straight edge out here, and that's going to be my shape. This is going to be a frustum. Now, what is the lateral surface area of this frustum? Well, if it was a cylinder, we would just take the circumference of that top circle. So we take a 2 pi r times the height of my cylinder. But now we don't have a cylinder, so we have to modify this a little bit. Here I really don't have just a radius. I have, well, a radius for the top circle, r1. I have a radius for the bottom circle, r2. So in general, really for the frustum, I should average those two values as part of this formula. And then instead of using the height for the lateral surface area, I'll take this distance here, the distance of that edge. So so we're going to call that distance L. So this could be the formula for the surface area of my frustum. But now if I look at my specific frustum, as in my slice over here, there's two things that happen when I apply this directly to my slice. One, I can put a very, very, very small slice, very, very thin slice. As the thickness of my slice gets smaller and smaller and smaller, the value of R1 and the value of R2 are going to get closer and closer to the same thing. So in the end, in the limit, I would look at 2 times whatever the radius value is divided by 2. So in other words, I can simplify this in my case to 2 pi just R here. The other thing I can look at is what is this distance on the edge over here? Well, in my case, that's this distance right here, and that's just the arc length of my curve. So I can replace that L with ds. And so this would be a small slice of that surface area. And so what do I want to do to find the total surface area? Same thing I've done before. I'm going to add up all my slices continuously. And this is really our formula for surface area. And this is the key formula to remember, although you'll see several different formulas in the book. So why are we going to see different formulas? Well, it's really because we've seen already two ways we could represent that ds piece. So you can imagine that I could have 2 pi r and then use my one value here, 1 plus dy dx squared dx, or I could simply use my other representation for ds, the square root of 1 plus dx dy squared dy. But the thing to remember is that in this first representation, this expression here will be some sort of function of x. It will be a function of x. So whatever I use to represent this radius value you need, I'll also have to have that radius in terms of x. Same thing over here. Over here I have, this is a function now of y. So if I decide to represent the arc length in terms of y, I'll have to find this radius value now as a function of y. And that could vary depending on which axis I'm rotating my curve about. All right, let's see if we can actually take this general formula now and actually apply it. All right, so here I have the curve y equals the square root of x. And we want to find the surface area if we took this curve and we rotate it about the x-axis. So I'm going to draw this picture over here, take this point, we're going to rotate it about the axis. This might be an example of one of the slices here. Here's a picture of my slice. Drawn a little sloppily, but there we go. So how do we find the surface area if we rotate this whole curve about this axis? Well, my steps I've written here are to first choose ds. And we're going to use the curve to make that decision. We want that in terms of x or in terms of y. After we make that decision, then we'll have to represent r in terms of our choice. So if we choose to represent ds in terms of x, then we'll have to use r as a function of x. So what do I mean by these choices here? Well, here's a little slice of arc length, and we said we could represent that one of two ways. I could represent that as 1 plus dy dx squared dx, or I could represent that as the square root of 1 plus dx dy squared dy. Now, it says use the curve to choose ds. Well, if my curve is given to me as a y as a function of x, well then it's very easy for me to calculate dy dx. In this case, that's 1/2 x to the negative 1/2, or 1 over 2 root x. So because I'm given y as a function of x, it's easy for me to calculate dy dx, and therefore it makes sense for me to use this expression for ds. So here I am calculating my surface area of this curve rotated about the x-axis. That's the notation I'm going to use for that. And it's going to be the integral of 2 pi r ds. And now I have used the curve to make my decision that I want to use 1 plus, Well, we said the derivative is 1 over 2 root x, so if I square that, I'll get 1 over 4x dx. And so now I just got to figure out what I want r to be. Well, the rest of this is a function of x, so now I need to represent r as a function of x. Well, here is what the radius is. It's this distance right here. And what do I mean represented in terms of x? Well, the idea is this equation y equals root x is describing the relationship between the y and the x values here. So I could say this height here is really the value y. It is the height to this point from the x-axis. We call that the y-coordinate. But because y is a function of x, I could also represent this distance with the square root of x. So there are two different representations for this same vertical distance. I could call it y and have it be a function of y. I could call it the root x and be a function of x. In this case, I need that radius as a function of x, so I will replace it with square root of x. And so now I have expression for the surface area. And we can go ahead and calculate this thing. We want to integrate this value from 0 to 4. Or I can just quickly open up Mathematica, where I have this all pre-typed out. And I'm just going to evaluate this cell. And I have this value of 361769. So 361769. Okay. But that's not the only way I could calculate the surface area. I could also calculate the surface area, if I wanted to, if I had made the other choice for a ds. Now I said that the curve is that y is a function of x, but we could actually solve that if we wanted to for x and say, well, this is also x equals y squared. It would be another representation for this curve. Now if I did that, I could certainly calculate dx dy, which in this case would be 2y. So now I'd have the integral 2 pi r, but now for ds I'm going to use 1 plus dx dy squared. So that would be 4y squared dy. But now it says, well, if I'm choosing to represent ds as a function of y, I need to represent my radius as a function of y. But the radius is that same distance, it's still the height. So now if I want that as a function of y, it would just be the value y. Now the last thing I have to consider is what are my limits of integration. Before I was integrating from x equals 0 to x equals 4. But now I'm integrating from y equals something to y equals something. So now I'm right here. I'd have y equals 0. But I have to figure out, well, what is the height when x equals 4? And I could certainly plug that into either of my equations here. So if y is equal to the square root of x and x is 4, then y would be equal to 2. So if I integrate this integral from 0 to 2, let's see what we get here. Once again, I have that pre-typed out in Mathematica. Here it is, the integral from 0 to 2, 2 pi y, root 1 plus 4y squared. We'll evaluate that, and sure enough, we get the same answer. So we can see that it doesn't matter which way we do it. In one case, sometimes the integrals will come out easier than the other, but in general, they'll get us that same value. Now the last thing we want to talk about is what happens if we rotate it about a different axis. So for instance, now instead of rotating with the x-axis, what if I rotated this about the y-axis? So I would take this point, and rotate it about this axis over here. Once again, I would be generating a surface area, but how would I calculate that one? Well, let's write that equation out. Surface area rotated about the y-axis, same starting point, 2 pi r ds, and once again I can choose how I want to represent ds. So if I wanted to, say 2 pi, and I wanted to use the 1 plus 1 over 4x dx representation, because remember, my surface, or my arc length slice, that's not going to change regardless of which axis I rotate about. That's going to be the same. And so if I want to represent in terms of x, here's the expression. But now I have to figure out my radius in terms of x. So here is my radius value right here. Now that's the distance from the y-axis over to my curve horizontally. So that would be represented by our x-coordinate. Now once again, if x is equal to y squared, that means I could also represent that same distance with y squared. And so those are my two representations for this horizontal distance, as x or y squared. In this case, because I've chosen ds to be in terms of x, I'll use the value x here. and integrate from x equals 0 to x equals 4. Now, lastly, if I took that same rotation here, rotated about the y-axis, but now I want to use my other expression for ds, well, I'd have 2 pi r, just like I always have, and now I have my other representation for ds in terms of y, and now I need this new radius value in terms of y. Now I would use my y squared value. So I'd have y squared in here, once again integrating from 0 to 2. And so these two values should be the same if we actually plug them into Mathematica. So now you've seen really all the variations of surface area. I can rotate about either axis and put either of them in terms of either variable. And so now it takes the practice of knowing how to represent each and not to get them confused. All right, so that concludes this video. Good luck.